Hello, everyone. Today we're going to be diving into the first of our lectures on nomenclature, or more or less how we're going to name organic compounds. So today we're going to go ahead and start off by looking at alkanes. But the first major question we should have is, what the heck is nomenclature? So when I'm talking about nomenclature, what we're really talking about is the need in any scientific field to develop a very specific set of vocabulary. So this is a way so that everybody can have a common language when talking about their area of interest. Now, this is going to be true no matter what your scientific field. Now, one of the problems is when I'm talking about things, I can't always use common names. They're often useful, but they can vary widely in between regions, cultures, vernaculars, languages, so can become a bit of an issue. And one of the great examples of this is a beautiful plant that you might know as wolfsbane. It's this nice blue flower. However, it is also known as monkshood, leopard's bane, and devil's helmet, and blue rocket. All of these are known common names. And the same thing kind of happens with chemistry. So for chemistry, these common names were often based on where their chemical originally came from or some sort of historical artifact. So some good examples of this are vanillin. Wonderful compound. We'll be playing around with it in lab for a couple weeks later this semester. It was derived from the vanilla bean, where it was obtained from extracts, and what gives vanilla its characteristic flavor. Similarly, we have morphine, which was originally derived from the poppy and thus uses the name Morpheus, or from the god of sleep, which again would help take away the pain. Now, one of the one of the things that we really need to is, because we have all of these inconsistency, we need to have a body that sets a given set of nomenclature. So going back to wolfsbane, thankfully, biology has committees in charge of setting scientific names. And these, in the case of biology, these plant or species names are often based on Latin. So, for example, if I'm looking at wolfsbane, this is often known as the genus Aconitum, again, coming from its blue character. Now, if I go to chemistry, chemistry has the International Union of Pure and Applied Chemistry, also known as IUPAC. They're in charge of several set of standards, but most famously, they're the ones in charge of setting names. So the class of nomenclature I'm referring to today is also known as IUPAC nomenclature, as this is the names assigned by the IUPAC governing committee. And they've been in charge for about 100 years now. And their goal is to make sure that every single chemical has one standard name that you can identify from around the world, and that it is unique, that no other chemical will share that exact name. That way we can have a very precise language when talking about molecular species. And the way we do this is by taking a molecule and naming each piece of the molecule one by one. So the way we do this is first start by looking at the longest continuous carbon chain in the molecule, and then look at each of the substituents and functional groups that are attached to that molecule. So as a result, the most important names to know are going to be those alkane names, as these will form the root of any sort of subsequent molecule. So because these carbon backbones often are formed by alkane, these are going to be the base name of the structure. And each of these alkanes will contain a suffix that ends in ane. Whenever you see ane, you should know that you're dealing with some sort of alkane or alkane-derived species. The first half of the name will tell you exactly how many carbon atoms are in that carbon chain. So for example, if we're looking at our first 4 alkanes, one of the important things to remember is that meth eats people's brains. It's a public service announcement and a good mnemonic, because this will help you remember the first 4 alkane names. The first is meth, which is 1 carbon. However, we have a 2 carbon species, this becomes an eth. Then for 3 carbons, it's prop. And for 4 carbons, it's but. So if we look at, again, these first 4 alkanes, that means that my first 1 carbon species is methane. and then 2 carbons is ethane. Then when I get up to 3 carbons, we go to propane, and then finally butane. Now, all 4 of these species are quite commonly used in everyday life, such as a propane oven or methane, as in natural gas. Now, again, this can help provide some context for those common names that you encounter. Now, if we go to larger molecules, we have a nice extra advantage here. So for alkanes, 5 carbons, atoms and longer, you can use your geometric shapes as a guide. So for example, pentane is 5 carbons long, as in a pentagon. Hexane is 6 carbons, as in a 6-sided hexagon. This last one you encounter less, but there is such a thing as a 7-sided heptagon. The octagon is a good old classic American reference point with 8 sides, and the nonagon and decagon. So again, using these as a reference point. Now, each of these 10 alkanes are really common, and you'll see them throughout the semester. So I will ask you to memorize these 10 names, as they may show up spontaneously as part of another question any point in the semester. Now that we have these root names, we can use these as the base to build up larger molecules. So I can use these alkanes as the backbone for a larger molecule by replacing one of the hydrogens with some other kind of substituent. So these are known as substituted alkanes. So that new structure is going to be based on the name of the original alkane. So if I replace a hydrogen on methane, I have a substituted methane. Or pentane would become a substituted pentane. Now, to really explore these, we need to look at some of our simpler substituents. So one of the most common class is going to be our halogens. So again, these are going to be our group 7 of the periodic table. These form a class of molecules known as the haloalkanes. So again, we have a halogen attached to an alkane. The 4 most common that we're going to be playing around periodically throughout the semester are going to be fluoroalkanes, chloro, bromo, and iodoalkanes. So again, each of these prefixes represents exactly what I've attached to the alkane. And that's exactly how we name these species. If it contains a fluoro, it becomes a fluoroalkane. So in this case, we have fluoromethane, chloromethane, bromomethane, and iodomethane. However, one of the things to watch out for, in this case, the nomenclature is relatively straightforward, as there's only 1 carbon atom we can attach to. However, as that carbon chain gets longer, I have to designate exactly which atom the molecule is attached to. So as long as there's only a single halogen, we can use a nice simple set of rules. The first is going to be identify how long my main chain is. In this case, I have a 5-membered chain, so that means I'm dealing with a pentane. This is going to be that root name of the molecule. Then we're going to, just like before, add the name of the substituent. So I've got a chloropentane. Now, this third step is the real tricky one, and that's going to be numbering the carbon atoms. So in this case, we're going to start by a terminal end and then work our way down. However, note that we have 2 different ends. So this could be either a 1,2 chloropentane or a 1,2,3,4 chloropentane. When we have to choose in between these 2 species, we're always going to choose the one with the lower number. So this is a 2 chloropentane as opposed to a 4 chloropentane. We're going to then add that locator number at the beginning of the molecule. So it's 2 hyphen chloropentane, no spaces, 1 word. Now, one of the problems we have is that I may have more than 1 halogen attached to my alkane. So in this case, I still have my pentanes, and that chlorine's in that same position. But by adding that extra fluoro, I've changed the molecule. So in these cases, we need some extra special rules. So the first is that we're going to set our numbering based on if any atom is on that C1 carbon. So in this first case, I have a fluorine atom on a terminal carbon. So this is going to be my C1. This means I have a 1 fluoro, 4 chloro species. However, for these other two cases, note we have no terminal halogens. So then I have to go in and identify if something is at the C2. If nothing's at the C2, I continue this process. Now, in both of these two remaining cases, I have something on the C2. So for this second case, I have a 2-chloro, 3-fluoro pentane. And then for this last case, we have a tricky case because if I go this way, I have a 2-chloro species. But if I start from the other terminal side, I have a 2-fluoro. So if you end up running into a tie, the lower number goes to the species that comes first alphabetically. So chloro is before fluoro, so we have a 2-chloro, 4-fluoro species. We can then take these prefixes and combine them into the general name by listing each of these positions with a hyphen preceding their prefix with a hyphen. Then I'm going to write each of these prefixes in alphabetical order separated by the hyphen. So in each of these cases, chloro comes before fluoro. So I'm going to list the chloro species first. So in this first case, the chloro is at the 4 position, while the fluoro is at the 1. So it's a 4-chloro, 1-fluoro pentane. The second species, we have a 2-chloro, 3-fluoro. And then in the final case, we have a 2-chloro, 4-fluoro pentane. And again, each of these cases, we separate each of those prefixes with a hyphen and no spaces, one continuous line. Now, if I've got multiple atoms of a single substituent present, I have to use something called a multiplying prefix to show exactly how many of those substituents is present. So notice in this case, I have 2 fluoros. So that would mean I have a difluoro species. And then what we can do is then list the position of each of these substituents separated by a comma as part of that series. So in this case, I have substituents on the 1 position on this terminal carbon, but none on this terminal carbon. So this will be my terminal species. So this means that I have a 1, 2, 3, 4, 5, 6. So I have a hexane species. I've got the fluoro at the 1 and the 4 position. So it's 1, 4 difluoro. Telling me exactly where that I have 2 fluoros and fluorine atoms and exactly where each of them is located. I can do the same thing with the chlorine. Notice I've got 2 chlorines at the 1 position, 1 at the 3, and then 1 at the 5. So I can continue. This is 1, 1, 3, 5 tetrachloro chloro. Now I have to bring all of these together. And again, I'm still going to list them alphabetically based on the substituent. So even though di comes before tetra, chloro still comes before fluoro. So this is a 1, 1, 3, 5 tetrachloro 1, 4 difluorohexane. So again, the real trick is we take each of these bits of the naming process, start with the main chain, identify your substituents, add them together in a big list separated by commas alphabetically. Now we can use these same naming conventions for a wide range of other common substituents. One that we'll be seeing a fair bit this semester is called a nitro group. So again, this is an end attached to 2 different oxygens. Yes, we do have some formal charges, but the overall species is neutral. So these nitro groups are going to follow the same general rule as halogens. Biggest difference is that we are going to use a nitro prefix. Otherwise, same general rules. So for example, if I'm looking at this species, I first want to go ahead and start by identifying that I have a 6-member chain. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So I have a hexane. And then I have 4 nitros, so I have a tetranitrohexane, and it's at the 1, 2, 3, 4, 5. So 2, 3, 4, 5 tetranitrohexane. Now we can go ahead and do this for more advanced species that contain a wide range of substituents. So in this case, I have 5 carbons. So 1, 2, 3, 4, 4 carbons. So I have a butane. I can then go ahead and take a look at those bromos. So again, I have a halogen at both carbon atoms, but I have more substituents at this end. So we have a 1, 2, 3, 4 tribromo bromo species. And then if I look for the nitro, that's at the 2 position. So, and then I have those 2 iodines at the 1 position. So I have a 1,1 diiodo. So when I put this together, I have a 1, 3, 4 tribromo, 2 nitro, 1,1 diiodo butane. Again, listing everything based on alphabetical order, BNI. All right, so that brings us to the end of our simple alkanes. Next time, I'll be talking about more advanced alkane species. Until then, take care.